Hello everyone, this is lecture 13 in real analysis, and in this lecture we're going to prove that the set of rational numbers Q is countable. So we're going to do this in steps. First of all, we will define the composition of functions and discuss their properties. We will talk about equivalent sets and their properties. We will explain why the Cartesian product n cross n is countable, where n is the set of all natural numbers. We will prove that the countable union of at most countable sets is at most countable. We will prove that Q is countable, and finally we will discuss why the set of real numbers is uncountable. So please like, subscribe, and comment on this video to support this work. So let us go ahead and define the composition of functions. So by the way, we discussed functions and their properties in a different video, which is linked down below in the description to this video. So suppose we have a function f from a non-empty set x to a non-empty set y. And suppose we also have a function g from the set y to the non-empty set z. So if we have a point little x in the set capital X, the function f is going to take this little x to the value f of x. And this f of x is going to be in the set y. And so since the function g is from the set y to the set z, it will take the value f of x to the value g of f of x. So this value g of f of x is the value of the composition of the function g composed with f at the point x. So now we can give a formal definition of the composition of two functions. So let x, y, and z be non-empty sets. Let f be a function from x to y. Let g be a function from y to z. Then the composition g composed with f is going to be a function that takes the set x to the set z. So the composition g composed with f acts from the set x to the set z, and it is defined by this formula: g composed with f at x is g of f of x for every x in the set capital X. So for example, the function sine of x squared is a composition of two functions, f of x equals to x squared and g of x equals to sine x. So the composition g composed with f of x is g of f of x, which is g at x squared, which is sine of x squared. And both functions f and g are from R to R. So let us discuss properties of the composition of functions. So it turns out that the composition of two one-to-one functions is one-to-one. The composition of two on-two functions is on-two. And the composition of two bijections is a bijection. So by the way, we discussed one-to-one on two functions and bijections in a separate video, which is linked in the description to this video. So we are not going to give the formal proof of this theorem. We are going to discuss the statement II just to get an intuitive understanding of why this statement is true. So suppose we have a function f from the set x to the set y, and suppose we have a function g from the set y to the set z. And suppose that f is onto and g is onto. So we want to show that the function g composed with f, we want to show that that function is onto. So let us take a point z in the set capital Z. Because the function g is onto, there will exist y in the set capital Y such that z is equal to g of y. So this is just by the definition of onto function. So now let us look at the point y in the set capital Y. Because the function f is onto, there exists a point x in the set capital X such that y is equal to f of x. So now let us see what is g composed with f at the point x. This is going to be g of f of x. but f of x is equal to y, so this is going to be g of y, and g of y is equal to z. So for this point z in the set capital Z, there exists a point x in the set capital X such that g composed with f at x is equal to z. But that means precisely that the function g composed with f is onto. So this is not a formal proof, but rather an illustration of the statement II. I hope that this illustration was helpful. So let us now talk about equivalent sets. So let us give a definition. Suppose we have two non-empty sets A and B. We say that they are equivalent, which we denote by A wiggle B, so A equivalent to B, if there exists a bijection F from A to B. So for example, suppose that the set A is the set of all natural numbers and the set B is the set of all even numbers. So then there is a bijection F from A to B defined by f of n is equal to 2n. So we are not going to check that this is a bijection, but you can take my word for it. So these two sets, A and B, are equivalent. So the equivalence of sets is a relation. So that means that for non-empty sets A, B, and C, the set A is equivalent to itself. If A is equivalent to B, then B is equivalent to A. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. So let us discuss the statement III. So if the set A is equivalent to the set B, then there is a bijection F from the set A to the set B. And if the set B is equivalent to the set C, then there is a bijection G from the set B to the set C. So then we can look at the function G composed with F from the set A to the set C. This function is a composition of two bijections, so it is a bijection itself. And so since there is a bijection from the set A to the set C, we can say that A is equivalent to C. So this is how we prove the statement III. So let us discuss some further properties of equivalent sets. So we have this theorem. So suppose we have two non-empty sets, A and B, that are equivalent. Then if A is finite, then B is finite. If A is countable, then B is countable. If A is at most countable, then B is at most countable. If A is uncountable, then B is uncountable. So let us discuss how we would prove statement 2. We are not going to give a formal proof, but we are going to discuss how the proof would go. So if the set A is countable, that means that there is a bijection from the set of natural numbers to the set A. So this F is a bijection. The fact that A and B are equivalent means that there is a bijection from the set A to the set B. So G is a bijection. But then G composed with F is a bijection from the set of natural numbers to the set B. But that means that B is countable. So this is how we show statement 2. So if the sets A and B are equivalent, and if the set A is countable, then the set B is countable. So let us now discuss how we would prove that the set n cross n, that the Cartesian product of n with itself, is countable. So just to recall, the Cartesian product of n cross n is the set of all ordered pairs Km, where K is a natural number and M is a natural number, and these ordered pairs can be depicted as these points on the plane. So in order to show that n cross n is countable, we need to show that there exists a bijection F from the set of natural numbers to n cross n. So let us look at the diagram over here. So basically, to construct a bijection from the set of natural numbers to n cross n, we need to visit every point of the Cartesian product n cross n. So we can begin with point 1, 1. and we can assign that f of 1 is equal to 1, 1. Then we can visit the point 2, 1, and we can assign f of 2 is equal to 2, 1. Then we can visit the point 1, 2, and we can assign f of 3 is equal to 1, 2, and so on. So you get the idea. So these arrows tell us the order in which we should visit the points in the n cross n, and this is how we can define the function f from n to n cross n. And we are not going to prove that this function is a bijection. You can take my word for it that this function is a bijection. So since we can construct a bijection of this kind, then the set n cross n is countable. So before we prove the next statement, we need to recall a few things. So a set A that is non-empty set, it is at most countable if it is either finite or countable. A set A that is in a non-empty set is at most countable if and only if there exists an onto function f from the set of natural numbers to the set A. So let us now consider this lemma. So let aj, where j is a natural number, be a collection of at most countable sets. Then the union over all natural numbers j of aj is at most countable. So basically, if we have a sequence of sets A1, A2, A3, and so on, and if every set in this sequence is at most countable, then if we look at the union A1, union A2, union A3, union, and so on, then this union is going to be at most countable. And just to recall that the union over all natural numbers j, aj is going to be the set of all x such that x is in some set ag for some j natural number. So to show that this union is at most countable, we need to show that there exists an onto function f from the set of natural numbers to this union, right? Because we have just recalled a few minutes ago that a set is at most countable if and only if there exists an onto function f from the set of natural numbers to the set. So in order to construct this function f that we are looking for, let us try to understand what we have at our disposal. So we have these sets aj where the index j is in the natural numbers, and each one of these sets is at most countable. So we have the situation that the set A1 is at most countable. That means that there exists an onto function f1 from the set of natural numbers to A1. The set A2 is at most countable. That means that there exists an onto function from the set of natural numbers to A2. So we call that function f2. And in general, every set aj where j is a natural number is at most countable. That means that there exists an onto function fj from the set of natural numbers to aj, and so on. So to summarize, for every j natural number, there exists an onto function fj from the set of natural numbers to aj. So now let us stop and think for a moment how we could use these functions fj to construct our function f. So the values of the function fj at k, where j, k are natural numbers, they depend on the two indices, j and k. So we can define a function that depends on two variables, j and k, and the value of this function h is going to be fj at k. And how is that helpful? Well, this function h is defined on the set n cross n, so on the Cartesian product n cross n, and it acts into the union of all of the sets aj's. And so you may say we are looking for a function f that is defined on the set of all natural numbers, and what we see here instead is that the function h is defined on the set of the Cartesian product of natural numbers with itself. But that is okay, because remember we discussed that the Cartesian product of n cross n is countable. So there exists a bijection G from the set of natural numbers to the set n cross n. And so if we compose the function G with the function H, if we look at this composition, H composed with G, this is going to be a function that acts from the set of natural numbers to the union of all AJs. And so this function H composed with G is going to be our function f. So all of this scribbling was scratch, of course, because this is not a rigorous proof. So we needed to think a little bit how to proceed with the proof. Now that we have a proof strategy, we are going to write a clean and nice proof that there exists a function f and onto function f from the set of natural numbers to the union of all AJs. So as we discussed, let us define a function h from the Cartesian product n cross n to the union of all of the AJs, and this function h is defined by the formula h of jk is equal to fj of k. What we want to show is that h is onto, right? Because this function that we are trying to construct, this function f, it has to be onto. So what does it mean that the function is onto? So suppose this is our n cross n. This is our union of all AJs, and this is our function h. So this function h is onto if whenever we take a point x in the union of all AJs, there exists a point j comma k in n cross n such that h of jk is equal to x. So let us try to show that our function h is onto. Let x be in the union of all AJs. We want to show that there exists an ordered pair jk in the set n cross n such that h of jk is equal to x. So since the point x is in the union of all of the AJs, it must be in one of those AJs, in one of those sets, because it's in the union. So there exists j natural number such that x is in AJ. But let us recall that AJ is at most countable, so there exists an onto function fj that acts from n to AJ, and we already denoted this function by fj. So the function fj from n to AJ is onto, so for this x in AJ, there exists a natural number k such that fj of k is equal to x. But fj of k is h of jk. But then h of jk is equal to x, and this is exactly what we wanted to show. We found two indices, j and k, such that a of jk is equal to x, and so this proves that the function h is onto. So we have an onto function h over here from the set n cross n to the union of all AJs, and what we are looking for is an onto function f from the set n of all natural numbers to the union of all of AJs. So just as we discussed, we are going to use the fact that n cross n is countable. So because the set n cross n is countable, there exists a bijection from the set of natural numbers to n cross n. So we have this situation here. So the function g from n to n cross n is a bijection, and the function h from n cross n to the union of all AJs is onto. So the composition h composed with g from n to the union of all AJs is going to be an onto function, because bijection is an onto function, h is onto function, and we discussed that the composition of two onto functions is onto. So then this function f that is equal to h composed with g from the set of all natural numbers to the union of all AJs is onto. So therefore this union of all AJs is at most countable, and this is what we wanted to show, so this finishes our proof. So finally, let us prove that the set of all rational numbers is countable. So let us recall that the set of all rational numbers is the set of all fractions, p over j, where p is an integer and j is a natural number. So let us consider these sets. The set A1 consists of all fractions p over 1, where p is an integer. The set A2 consists of all fractions p over 2, where p is an integer. The set A3 consists of all of the fractions p over 3, where p is an integer, and so on. So for every j natural number, the set AJ consists of all fractions p over j, where p is an integer. So we may notice that Q is the union of all of the sets AJ. So by the previous theorem, if all of the sets AJ are at most countable, then Q is at most countable. But let us look at these sets AJ. So A1 is actually the same as the set of all integers, and we proved in a previous video that Z is countable. And the video in which we prove that Z is countable is linked in the description to this video. The set A2 is not equal to Z, however, it is equivalent to Z because we can easily construct a bijection from the set A2 to Z. All we have to do is to take the elements of A2 and multiply them by 2, and we will get elements of Z. So, and Z is countable. And we stated earlier in this video that if we have a countable set and if we have another set that is equivalent to a countable set, then that set is countable. So A2 is countable. So similarly, A3 is equivalent to Z, which is countable. So A3 is countable. And in general, for every j natural number, AJ is equivalent to the set of all integers is countable. So Q is the union of countable sets. So by the previous theorem, Q is at most countable, which means that Q is either finite or it is countable. So we are going to leave it as an exercise to show that Q is infinite. So since Q is infinite, it cannot be finite, so Q is countable. And that finishes our proof. So let us finish this video by recalling that the set R is uncountable because it contains the interval 0, 1, and in a previous video we proved that this interval 0, 1 is uncountable, and that video is linked in the description to this video. And the set R is a union of all irrational numbers, so this is the set of all irrational numbers, with all of the rational numbers. So the set of all of the rational numbers is countable, so the set of all of the irrational numbers must be uncountable for R to be uncountable. So the set of all irrational numbers is uncountable. And that finishes our video. Thank you for watching it. This video was a little bit longer than the previous one because I wanted to make sure that all the details were covered so that you could follow them easily. It is important for me to hear from you. It's really encouraging to read your comments. So please comment on this video, write what you liked about it, and what topics you would like to be covered on this channel. Like this video, subscribe to this channel, and support this work. And be good at math.